we're going to talk about Wilson's theorem today, and it's a theorem that follows from Fermat's little theorem. So this theorem itself says if p is prime, then p divides the quantity of p minus 1 factorial plus 1. Now let's go ahead and set out to prove it. Just like the last example where we used beads, strings, and bracelets to solve the problem, we're going to use a different analogy, this time circles and polygons, to solve our problem. So let's get started. So first, to solve our problem, we're going to assume that we have p is prime, and we separate a circle into p parts of arcs. So in this case, p is 5, so p equals 5, and you can see I separated this circle into 5 smaller arcs. So what I'm going to do now is we're going to figure out how many different polygons we can make. So what I mean by this is, here's one possible polygon. And a polygon in this case, the rule for making it is you find a starting point, and then you go to some next point, and then you go to some next point that you didn't already go to, and you can cross over. So you go to some next point, then we go to some, then we have to go to some next point, and then now we have covered every point, and we just return to our original starting location. So this is called a stellated pentagon. Okay, and it's called stellated because it's made using this process. So now what we're going to do is we're going to figure out how many different polygons we can make. So for example, how did we make this? We started at the point 1, and from 1, how many options did I have? I can either go to 2, 3, 4, or 5. So I had 4 options. So 4. And then, well, actually, to begin with, I had 5 I could start with. So it's actually 5 times 4. So I picked 1. And then after I pick that one, 1 is already taken. So I only have 3 left. 3 times 2 times 1. So it's basically p factorial. But that turns out we've overcounted some cases, because let's say we start at 1. This polygon we see here could have been made in a multitude of different ways. For example, I went like this. I came here, and I think I went down here, this way, down here, and then back up. But I could have just as easily started at 1, and I could have gone this way, could have gone up here, I could have gone this way, I could have gone down, and I could have gone up. And I could have also made this polygon by starting at 5 and following a path and following the different path. So what we have to notice is from 1, there's 2 different paths I can take to make it. From 5, there's 2. There's 2 here, 2 here, 2 here. So we have to divide this p factorial by 2p, and that's the total number of stellated polygons, stellated pentagons that we can make using this process. So this is our first result, and we'll use it a little bit later. Now we want to find the number of regular stellated pentagons we can make. And regular stellated pentagons mean that we can rotate it. So what we need to do again is we have to create a circle, and I'm just going to use my water bottle thing here to create a circle. So here's my circle. So here's my circle. And again, I'm going to draw in my 5 points. So I'm going to draw them roughly. So here, 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 here. There's my 5 points. So now we're going to draw a regular stellated pentagon. And that's done. There's 2 of them. Here's the first one I'll draw. It's basically just a pentagon. Like this. And this is called regular. I know it's not perfect, but it's called regular because I can rotate it just 1 arc length. So if it was p, then it would be pi over p degrees. I could rotate it that much, and it would look exactly the same. And the other one looks like this. It's just a star. The other one is a star. And again, you can see if I rotate the star just pi over p degrees in the circle, it's going to look exactly the same. And it turns out that there are exactly p minus 1 over 2 regular stellated polygons for each p we choose. And we can prove this real simple by using our case right here. Let me use a different color just for simplicity. So let me take this and come down here. And notice that p is either, the only even prime number is 2, and we can see that fits for this because 2 divides 2 minus 1 factorial, 1 plus 1. 2 divides 2, and every other prime number is odd. So we can assume that p is odd. So that means that when we draw the points, there's going to be an odd number of points, and we're going to have this when we draw the vertical line, it's going to fall between 2 points. So we can form a regular stellated polygon by using this process. To form the pentagon, I went from one point to its neighbor. I didn't skip over any points. So I skipped over 0 points, and I just formed it. Now, to make the star, I skipped over this point, and then once I got here, I skipped over this point. Then once I got here, I skipped over this point, and so on. So I skipped over 1 point. And what if I skipped over 2 points? So if I started here and I skipped over this one and this one, I would come here. But now I'm just forming the star again. So if any of my skippings lead me to go on this side of the vertical line, I'm just repeating myself. So it turns out there's only 2 cases, and if we plug in 5 into this formula for p, we get 5 minus 1 is 4, divided by 2 equals 2. So we can see this formula is correct. So I'm going to grab another piece of paper. So now we're just going to continue with our proof. So now let me just recap the facts. We know that there are, let me check my paper. There are p factorial over 2p total stellated polygons. And we know that p minus 1 over 2 of them are regular. So if we subtract, we get the stellated polygons that are not regular. And now what we're going to do is we're going to find out if p divides this. And it turns out it does, because if we just look at this one that I drew initially, this one is part of a family of ones that look like this. So actually what we can do is we can rotate this. So for example, let's pretend I'm rotating the circle. So I'm going to rotate it. Let's make a reference point, and I'm going to rotate this is about the center right here, and I'm going to stop when I get to, here's one from my previous video. So this is my reference point. So I'm going to make this line up with this, and I'm going to rotate about this. So this moved a little bit. Let me put it back. So I'm going to put it over here. So it's lined up with that. So now look at it this way, and you'll see that there's the second one. Now I'm going to use that same reference point and line this up to it. There's my third one. So you need to look at this as if it's horizontal, as if this is the one I drew in the beginning. And then we're going to rotate this again. Don't worry, I can still see the reference point. This is the fourth one, and then rotate it again. This is the fifth one, and coming back, that's the one we started with. So see how, since there's 5 points, there are 5 different 5 different stellated pentagons that we can make. So they naturally fall into groups of 5, or groups of p. So that means that implies that this quantity is divisible by p. And remember, this represents all the ones that are not regular. So it does p does divide it. So now we're going to clean this up a little bit, and we're going to get, if we clean this up a little bit, then let's try to find a common denominator up here. We're going to get p factorial minus, I'm going to multiply each of these by p times p minus 1 over 2p squared, incorporating this p. Now we're going to take out a p and everything. So if we take out a p from here, and p from here, we get p minus 1 factorial minus p minus 1 over 2p. So notice that 2p divides this quantity, and that means that, notice that if 2p divides something, then p also divides it, because if 2p divides it, that means 2 divides it and p divides it. So p minus 1 factorial minus p plus 1, p divides that. And it's pretty obvious that p divides p, so we can take it out. So p minus 1 factorial plus 1 over p. So that means that p divides p minus 1 factorial plus 1. And notice we did this step because I can break this up as p minus 1 factorial minus p plus 1, all of them over p. And this is pretty obvious, so we can just cancel it out. So it has to be an integer. Okay, so now last thing, we have proven the theorem, because Wilson's theorem said that p divides p minus 1 factorial plus 1, and that is exactly what we have right here. And last thing to note is, why does p have to be prime? Why can't it just be a composite number? Well, this is why. The problem arises, let's use, I'm going to use the edge of this. The problem arises when we're in that process of finding the regular ones. So for example, let's just draw a circle, really fast circle. So pretend we're trying to find the regular stellated ones. Let's just choose a composite number such as 6. So 1, 2, 3, 4, 5, 6. Now let's do the skipping thing again. So coming down here, this is a composite number. I did the vertical line thing, then I'm going to skip 0, and that's fine because then I just get my hexagon. What if I skip 1? Then we're skipping that one, skipping this one, skipping this one. Let me do this in different colors so it's obvious what I'm doing. And notice that it just keeps going, just keeps repeating over and over again, this infinite triangle. And that is definitely not a hexagon. So it's not a stellated hexagon, so we get problems. So we can't do it for composite numbers. It has to be from prime numbers. And we'll see some applications of this in a while.